Today we discuss important topics of calculus. We also previous class discuss directional derivative and partial derivative and derivative and also Jacobian of function and also linear operator and operator we also discussed in first class. So today we talk about some result and obviously we prove some result right here. Let phi not equal to C subset of Rn and interior of C not equal to phi and interior of C not equal to phi. Then let P belongs to interior of C, and if C to Rm and if C to Rm be a function such that if dash Cu exist, okay, for some u belongs to Rn, then first one, if dash Cu belongs to Rm, and second one, if dash C0 exists always and is equal to 0, exists always and is equal to 0, belongs to R to the power m. And number 3, if Rn to Rm is linear operator, then f dash Cu will be Fu. Okay, so we also discuss last, we also known about f dash Cu, and obviously known f dash C exists always and equal to 0 because direction is 0, fc minus fc, so this one is 0. So now we're going to last one. This f dash Cu equal to how much? Equal to limit t tending to 0 f of c plus tu minus f of c here t. Okay, then this one equal to limit t tending to 0 f of c plus tu difference c by t. This one equal to limit t tending to 0 f of tu divided by t. This equal to limit t tending to 0 t of f of u by t equal to f of u. Okay, for all u belongs to Rn. Okay, for u belongs to Rn, also discuss this one. Okay, then what we find from here that if u exist, okay, that means if dash Cu exist in all direction u belongs to Rn. That is, f dash cu is a mapping. F dash cu is a mapping from Rn to Rm. Rn to Rm. Okay. So f dash cu equal to fu. So f dash cu equal to fu. Okay. Now we erase that portion and going to proof of another proposition. Okay. Now we're going to give some proposition. Now let f of c1 subset of Rn to Rm and c2 to Rm and c2 subset of Rn to Rm be two functions. Okay. Let p belongs to interior of c1 c2 such that if dash pu and g dash pu exist for u belongs to Rn. Then alpha f plus beta z there phi u equal to alpha f dash pu plus beta g dash pu. Okay. Then what happened? Then we write proof of this. Okay. Now we write proof. Note that f dash pu equal to limit t tending to 0 f of p plus tu difference f of p by t and g dash pu equal to limit t tending to 0 g of p plus tu difference g of p by t. Okay. Then alpha f plus beta z whole dash pu equal to limit t tending to 0 alpha f beta z p plus tu difference alpha f beta z p by t. Okay, then this one equal to limit t tending to 0 alpha of f of p plus tu difference f of p plus beta of g of p plus tu difference g of p by t. Okay, then what happened? We erase our portion and going to forward. Limit t tending to 0 or alpha f of p plus tu difference f of p by t plus beta g of p plus tu difference g of p by t. Okay, then this equal to alpha f dash pu plus beta g dash pu. Okay, then what happened? Then we also see that du alpha f beta g equal to alpha tu f c, here c, and beta tu gc. Okay, then next we go to another proposition. We go to another proposition. Okay, now we also going to another proposition. We write here. Okay, let f C subset of Rn to Rm be a function and C belongs to interior of C such that f dash cu exist in the direction of u belongs to Rn. Then limit t tending to 0 f of c plus tu equal to fc, that is f is continuous along the line c plus tu. Okay, so we now prove this one right here. then if just cu equal to this one. Okay, define phi t equal to f of c plus du and phi of 0 equal to f of c. Then if just cu equal to then f dash cu equal to limit t tending to 0 phi t difference phi 0 pi t, okay, equal to phi dash 0. This one exists. Then phi is differentiable at 0 and hence continuous at 0. And hence continuous at 0. That is limit t tending to 0 phi t equal to phi 0. Okay. Next we also discuss this problem. Now we also going to definition of derivative. Okay. It is this portion and going to definition of derivative. Derivative. Let f C subset of Rn to Rm and C belongs to interior of C and C belongs to interior of C, then there exists an open ball VRC subset of interior of C then C plus H belongs to VRC where norm is equal to less than R. Okay, then a linear operator A, then a linear operator A r to the power n to r to the power n is said to be is said to be derivative of f at c if limit norm of h tends to 0, norm of f of c plus h difference f of c difference ah by norm h equal to 0. The derivative of f at point c is denoted by f dash c or d of fc. Okay, so derivative of f at c be an operator. Okay, we'll also discuss later in epsilon definition, epsilon delta definition. We erase this and also going to epsilon delta definition. Okay, C be a non-empty subset of Rn. C be a non-empty subset of Rn and C belongs to interior of C. Then there exists R greater than 0. Then there exists R greater than 0 such that PRC subset of interior of C and CH and C plus H belongs to BRC. Okay, if H belongs to Rn and norm H less than R. Okay, then what happen? Then if there is a linear operator A such that if there is a linear operator A Rn to Rm such that limit norm of H tends to 0, norm of f of c plus H difference f of c difference ah by norm of H equal to 0. Then A is called derivative of f at c. Then A is called A is called derivative of f at c, and f is called differentiable at point c, and a equal to f dash c or d of f c. Okay, then then a is derivative at point c. A is derivative at point c if for each epsilon greater than 0, there exists delta epsilon c such that such that delta less than r, norm of f of c plus h, difference f of c, difference ah, less than epsilon norm of h. Okay, for all h belongs to Rn with norm of h less than delta, then or norm of fx, difference fc, difference ax, difference c, less than epsilon norm of x, difference c. For all x belongs to Rn with norm of x, difference c less than delta. Okay, then this implies that limit x tending to c, norm of fx, difference fc, difference ax, difference c, divided by norm of x, difference c equal to 0. Okay, so we also discuss this one, how we handle this derivative. Okay, let's see non-empty subset, and a linear operator A is called derivative of f at c if this condition satisfied. If limit norm h tending to 0, f of c plus h, difference f of c minus ah by norm of h equal to 0, then here f of c plus h, difference f of c, difference ah, norm of this less than epsilon norm of h, then f of ax minus f of c minus f ax minus c less norm of this equal to less than epsilon norm of x minus c, then limit x tending to c, fx minus fc minus ax minus c by norm of x minus c equal to 0. Okay, so we also discuss this one. Now derivative of a function is unique also, we also discuss later. So in this class we discuss first some properties of derivative, and derivative function which belongs to Rm, and obviously if f is linear, then derivative is equal to fu, or f dash cu That means directional derivative at point C in the direction u is fu if f be linear. Then another proposition, alpha f plus beta g dash equal to alpha f dash plus beta g dash. Then again, limit t tending to 0 f of c plus tu equal to fc. That means f is continuous along the line c plus tu. And also definition of derivative and going to epsilon delta definition of derivative. Okay, so today we stop here.